So today we return to the discrete time Fourier transform, and prior to the midterm, we were talking about how is it that we can perform the discrete time Fourier transform? How do we compute them, both the forward transform, and we talked about the inverse transform. We haven't really applied that definition very much yet. Today what we want to do is finish up that discussion talking about the different ways that we will perform the transform and the inverse transform, and then that'll lead into talking about different properties of the discrete time Fourier transform that will help us with that process, and also properties that have implications and applications in system analysis. And so we want to reach that point where we have the background for next time when we'll be engaging how do we use the discrete time Fourier transform to do this system analysis, things that we formerly were only able to do in the time domain by solving difference equations or by doing a convolution. So that's what's ahead. So last time and the last two times we were really focusing on this first step. How do we use the definitions of the discrete time Fourier transform, and what is it? When does it exist? How do we use this summation formula to compute a discrete time Fourier transform or an inverse transform with the associated integral equation? Today we want to actually engage the method we're going to be more for the future, because we want this to be an easy process. We want this to be part of our system analysis technique. We're basically trying to move the process of system analysis out of the time domain into the Fourier domain using the discrete time Fourier transform so that the mathematics are easier. And that's really only a valid thing to do if the mathematics of getting from one domain to the other are simple. And so that's why we prefer to use lookup tables to do it. And we have two lookup tables for that, a transform table and a set of properties that will help us with that process. So we'll see how to engage that today and dig into a little bit more about what those properties are. And by the end, we'll get to a couple of properties that are actually going to give us an alternative way, a simple way to get to the frequency response of a system directly from the difference equation. And this is all parallel to the techniques we use in continuous time systems to do the same thing. So you're familiar with transform tables from other transforms like continuous time Fourier transforms and Laplace transforms. The discrete time Fourier transform similarly has these kinds of tables where we have on one side the time domain signal, in this case a discrete time signal, and on the other side the transform, the form of the analytical form of a transform of that particular style of signal. For the DTFT, you might have two different flavors of that. The cycles per sample, capital F digital frequency form, or if you're working in digital radian frequency, capital omega, there's a analogous form which is mostly just replacing 2 pi f, 2 pi capital F with capital omega. In some cases, there's an extra pi or 2 pi kind of factor that comes into play. But we want to be able to use these tables, and you'll notice a lot of the common signals that we use in our systems, exponential kinds of signals, unit sample signals, cosines and sines, sinc functions, unit steps. These will be the ones that will tend to show up in these transform tables because they're the ones we're going to be most commonly use. Now, the particular signals that we will be probably working with for forward and inverse transforms may not look exactly like this. They may be scaled versions. They may be time shifted versions. They could be compressed versions. And so we need a second table to tell us how to deal with those different operations that might be applied to either our time domain signals or to our transforms, and how that affects the transform process. So if we know what those different actions will do to the signals and to their transforms, we can expand greatly the list of signals that we can easily transform using these tables. And so that's the purpose of this. Now what we want to do today is not just look at these, how to apply these properties, but also understand where they're coming from, what they mean. As an example of, or a simple example of how we would apply the tables in a discrete time Fourier transform context, If we had our simple recursive system, the IIR feedback system that we've been analyzing a number of different ways, and a difference equation y of n equals x of n plus alpha y of n minus 1, so one feedback path here, where in order to be stable, alpha had to be a fractional value with a magnitude less than 1. We derived that its unit sample response is alpha to the n u of n. If we then wanted to know what is the discrete time Fourier transform of this of h of n, what is the frequency response of this system? We've done that analytically with the equation. If we wanted to do that more simply, we could have gone into our lookup table for transforms, and in fact, that form shows up in the transform table, alpha to the n u of n, as long as the magnitude of alpha is less than 1, has the transform, the same one we derived using the summation formula. And so we could have just gone in the table and gotten that answer readily, although we wouldn't have had all the fun we had with the infinite sum. Similarly, our two sample averaging FIR filter that was non-recursive, that has a difference equation y of n equals 1/2 x of n plus 1/2 x of n minus 1. We derived its unit sample response was 1/2 delta sub n plus 1/2 delta of n minus 1. Again, if we wanted to know what its frequency response was, we would be taking the discrete time Fourier transform of h of n. In this case, well, I have a table lookup for delta sub n. It has a discrete time Fourier transform of 1. And so this 1/2 delta sub n translates to 1/2 times 1 in the transform domain in the discrete time Fourier transform. This delta sub n minus 1, well, I don't have that exactly in my transform table, but I do have a properties table that says if you have a time shift, a time delay in your signal, you take its discrete time Fourier transform x sub f, and in the DTFT, you're going to multiply that by e to the minus j 2 pi mf, where f is our frequency variable and m is the amount we delayed our signal in the time domain. And so since I know the discrete time Fourier transform of delta sub n is 1, the discrete time Fourier transform of delta of n minus 1 is 1 times e to the minus j 2 pi 1 f, because our delay is 1. And since we had a 1/2 out in front, we have a 1/2 out in front again. So together, the total discrete time Fourier transform frequency response is the 1/2 plus 1/2 e to the minus j 2 pi f, again, something we derived using the definitions previously. So we want to be familiar with a number of these transforms for common signals and the properties, the theorems, and what happens to our discrete time Fourier transforms when we do things like making linear combinations, like multiplying by n, convolving things, multiplying things, time reversing, all those operations. Now, these aren't in your notes, but just reviewing, because we've talked about this in the past, there are certain symmetries we can count on in the discrete time Fourier transform when we take the transform of a real valued time function. If our x sub n is real, the discrete time Fourier transform of x sub n, call it x sub f, has to be periodic with a period of 1. The magnitude versus frequency is an even symmetric waveform, and the phase is an odd symmetric waveform, and that's because the discrete time Fourier transform of a real signal is what we call conjugate symmetric. It has conjugate symmetry, meaning it's generally complex, and x of minus f equals not x of plus f, as it would be for even symmetric, but x, the complex conjugate of x of f. Now for our signals, then that conjugate symmetry is what gives rise to having even symmetric magnitudes and odd symmetric phases. And again, that symmetry applies both around f equals 0 and f equals 1 and all the multiples of that, and also around the Nyquist frequency and its multiples. And if our time signal is real and itself is even symmetric in the time domain around index n equals 0, then the discrete time Fourier transform is completely real, has no imaginary part. And if we plotted that real function versus f, we'd get an even symmetric function of f. If we plotted the magnitude, it would still be even symmetric, and the phase would still be odd symmetric, but the phase would have to be only either 0 for positive real values of x of f, or plus or minus pi. So we have to be on the positive or negative real axis. And so when x of f goes negative, we'd plot its magnitude as positive, and we'd plot its angle as either plus pi or minus pi to account for that negative sign. So if x of n is real and even symmetric, we still have the even symmetry of the magnitude of x. But in this case, if I plot just x of f, the real discrete time Fourier transform function itself, allowing it to go negative, we would see that it is an even symmetric function, as is the magnitude and the phase. Similarly, if x of n is a real valued function in the time domain but has odd symmetry around index n equals 0, then its discrete time Fourier transform is purely imaginary, has no real parts. And if we plotted that versus frequency, we would get an odd symmetric amplitude spectrum. If we still take the magnitude and phase of that, the magnitude would still be even symmetric around f equals 0. The phase still has to be odd symmetric, but in this case, the phase has to be on the j-axis, the imaginary axis. So it either has to be in the positive j direction at plus pi over 2, or in the negative j direction at minus pi over 2. Now, in terms of properties of the discrete time Fourier transform, the DTFT is a linear operation. And so it has to obey the two principles of additivity and homogeneity, as those together make linearity. Since that's true, since the DTFT is a linear operation, the following relationships will hold. Because it's homogeneous, a homogeneous transform, if we take a time signal x1 and find its discrete time Fourier transform, we then scale x1 by some scalar value a, its discrete time Fourier transform scales by exactly the same scale factor. So multiplying things by scalars in one domain results in exactly the same multiplication in the other domain. Again, a is a scalar. It can't be a function of x, of y, of n, or f. It's just a numeric value. It could be real, imaginary, or complex. That doesn't matter. But it's just a scalar value. Likewise, discrete time Fourier transform is additive, which means if x1's discrete time Fourier transform is known and x2's discrete time Fourier transform is known, if I take the discrete time Fourier transform of their sum, that DTFT better look like the sum of the individual DTFTs. Together, those two properties, additivity and homogeneity, give rise to this property that if I do them together, if I scale and add multiple signals, I scale and add their discrete time Fourier transforms when I take the DTFT of the combination. And this is just a fancy restatement of superposition. So because it's a linear operation, superposition holds for the discrete time Fourier transform, just as it does for other Fourier transforms. That's what allowed us in that previous example when we had a delta sub n times 1/2. All we had to do was take its transform and multiply it by 1/2 because it was a linear operation. If we know the discrete time Fourier transform of a signal, but then we're presented with a time-reversed version of it, and by time-reversed, again, we mean flipped or folded around the n equals 0 axis, so that we're running it backwards in time compared to the other. What does that do to the Fourier transform? Well, as we saw in that example, well, if I take x of minus n, if I time reverse it, its discrete time Fourier transform, we replace f with minus f. Now, if your time function happened to have been real valued, which most of ours are, the way this will be manifested in is we may not be so obvious that we replaced f with minus f, but what we'll see is that we will have taken the complex conjugate of the discrete time Fourier transform, meaning the magnitude will be the same, but the phase will be flipped, or the imaginary part will change sign. That's what happens when we do a time reversal. Time shifting, we actually already applied this theorem. We looked it up on the table and applied it to our delta sub n minus 1 sequence. It applies both for time delays, where we have x sub n minus 2 shifts to the right, or time advances, if we had x sub n plus 2 shifting things to the left. Both obey the same principle when we take their discrete time Fourier transforms. If x sub n's transform is x of f, then if we time shift x sub n, if we delay it by m, its Fourier transform is multiplied by e to the minus j 2 pi mf, where capital F is our digital frequency, m is the amount that we delayed, and if we have a delay n minus m, we have an e to the minus j argument. If we have a time advance, we have an e to the plus j argument. Now, what does that imply happens to our DTFT when I apply a time shift to it? So shifting something or delaying it in time means we're going to take its spectrum, its discrete time Fourier transform, and multiply it by a complex exponential, an e to the minus j phase term, where that phase is changing with frequency. And we know when we multiply two complex quantities, two complex functions, what we have to do is take their individual magnitudes and multiply them together to get the magnitude of the product. And we take their phases of the individual ones that we're multiplying together, and we add their phases to get the phase of the product. So if we look at what multiplying the discrete time Fourier transform of our x sub n, what multiplying that by this exponential did due to the time delay, if we look at the magnitude of this delayed term, this e to the minus j 2 pi mf, as we've proven in previous classes, the magnitude of any complex exponential, because it's a cosine plus or minus j sine, when we take its magnitude, we always get 1, because it becomes the square root of the sum of a cosine squared plus a sine squared. So basically, delaying something in time has no effect on the shape of the magnitude of the discrete time Fourier transform. It only has an effect on the phase part. What effect does it have? Well, we're going to add the phase of this exponential term to the phase of our original signal, and this phase angle is the angle of e to the minus j 2 pi mf is minus 2 pi mf. So it's the exponential without the j. That's the phase angle part. It's a linear function of frequency. So if we were to plot this function versus f, it's a straight line whose slope is minus 2 pi times m. So that means if we've, well, that m in this case is the same as n0 in our delay. And so the bigger my delay, the steeper my slope. And if I have a time delay, I have a negative slope. If I have a time advanced, an n plus n0 or n plus m, that would be a positive slope versus frequency for the function. And so a time delay or time advance in the time domain does not affect the magnitude of the discrete time Fourier transform. It only affects the phase. And what it does is add or subtract a linear amount of phase that is the amount of phase we need to add or subtract in order to achieve the same time delay at all frequencies. And as we've shown before, that is a linear relationship. The higher the frequency, the shorter the period, and the more phase we need to achieve the same time shift. Now let's take a couple numeric examples to see how to apply this time shift in the context of trying to take an forward or inverse discrete time Fourier transform. And let's take a straightforward example that we've been using all along, one that we know well. If we have a time function that's a exponential, like a alpha to the n, u of n, we know its discrete time Fourier transform happens to be, we'll call it xp of f. That is 1 over 1 minus alpha e to the minus j2 pi capital F. Now, as an example of using our time shift, we could ask, what's the discrete time Fourier transform of alpha to the n plus 3, u of n plus 3? We want to know what's the discrete time Fourier transform of that. According to our property, this is like an alpha to the n u of n with a shift, with a time advanced by 3. And so we would start off with the alpha to the n u of n transform. Of 1 over 1 minus alpha e to the minus j2 pi f. And then we have to multiply it by an exponential that's dependent on our time delay here. In this case, an e to the plus j, because I'm doing a time advance, 2 pi times the amount of shift, which is 3, times f. And if you wanted to simplify that, it's an e to the plus j 6 pi f in the numerator over 1 minus alpha e to the minus j 2 pi f in the denominator. So that's a straight direct application of the time shift property. It can get a little trickier though. That one was straightforward because I had the same n arguments in every term in my function. If you don't have that, then I've got to be careful about how I apply the time shift property. For example, if we had something like this, where we had a alpha to the n minus 2, so it looks like a shift, but multiplied by a u of n, then we wanted to know what's the discrete time Fourier transform of that. This one I can't apply the time shift directly because both of my arguments don't have the shift in it. So I have to adjust these so that they are both have the same index values. And there's really two possibilities here. So we could, let's take an example just to keep it numeric. Let's let alpha be 1/2. And so if our x of n then was 1/2 to the n minus 2 u of n, I need this to be an n, or I need this to be an n minus 2. Let's make this an n. So this is like 1/2 to the n u of n. But I can't just ignore this. I have another factor that's 1/2 to the minus 2 out in front. And fortunately for me, this is just a numeric constant. So 1/2 to the minus 2, the minus sign flips this over to 2. The squared term makes it 4. So this is equivalent to 4 times 1/2 to the n u of n. And that we can easily transform that's just going to be 4 times, let's put that in the numerator, 4 over 1 minus 1/2 e to the minus j 2 pi f. So no time shift even in this one once I made it made the n arguments the same. Now, there was an alternative way to approach this one. If we look at these function, this is like 1/2 to the n, or 1/2 to the n minus 2, but starting at u of n. And so at n equals 0, that has a value of 4. At n equals 1, that has a value of 2, half as big. At n equals 2, that has a value of 1. N equals 3, it has a value of 1/2. And so on, just getting smaller and smaller and smaller. Now that's equivalent to the 1/2 to the n minus 2, u of n minus 2, a fully shifted version of it. Oops, come on. Which would account for everything up to this point. So to get this n equals 2, n equals 3, n equals 4, to get all of these points. I still have these other 2 points, so I can add those in. Plus 1/2 to the n is 1. Delta sub n minus 1. To pick up this one. And 1/2 to the n equals 0. Delta sub n to pick up this one. And now these we could all Fourier transform each of these individually and combine them together, where this one gives us our 1 over 1/2, or 1 over 1 minus 1/2 e to the minus j 2 pi f, with a time shift term, e to the minus j 2 pi times 2f. That would take care of this term. The next term would Fourier transform as well, let's see, this 1/2 becomes 2. This is raised to the minus 1 power. And so that's going to give us a 2 e to the minus j 2 pi 1 times f. And this last term is going to give us a 4, just 4, because the delta sub n transforms as a 1. And you can go through the algebra, but it turns out that when I combine these all under a common denominator, it will actually end up looking exactly like this. So either approach that you take, but the point is when we want to apply the time shift, all of the n arguments have to be the same before we can apply the time shift property. And if they're not, we need to modify the function somehow so that we are transforming one that only functions that have the same set of index arguments. Let's take an inverse transform just to see how it works in that context. So in an inverse transform, let's say we have a function that we want to inverse transform, and it happens to be this one. So 1 over 1 minus 1/3 e to the minus j 2 pi f, and that's quantity squared. And we want to know what's the time function, what's the inverse discrete time Fourier transform of that gives us some x sub n. And if we go to our DTFT table, look for something close. The closest thing we might find in a table would be this one, that n alpha to the n u of n transforms to alpha e to the minus j 2 pi f over 1 minus alpha e to the minus j 2 pi f quantity squared. So my denominators are right as long as alpha is 1/3, but the numerator's all wrong. So we need to adjust this so that it looks like this form and maybe has some multipliers after it that we can recognize as either just scale factors or time shifts or something like that. So let's take a look at how we could rewrite our x sub f. And we want it to look like this form. So we've already got the denominator part. That's good. 1 minus 1/3 e to the minus j 2 pi f and the whole quantity squared. So we're all set there. But I need in the numerator an alpha, and it looks like my alpha is 1/3. So I'm going to need an 1/3 up in there. And I need an e to the minus j 2 pi f. And now I have a form that I can transform, but that's not what my original function was. So I need to adjust this to get back to where I was. So first thing we need to do, we didn't have the 1/3, so let's multiply the whole thing by 3, which will get rid of that. I need to get rid of the e to the minus j 2 pi f, so we can multiply by e to the plus j 2 pi f. And now I hope you'll agree that when I combine these together, I get back to my original time function. But we now can inverse transform this. This part's going to give us an x sub n that's going to transform to some n times 1/3 to the n u of n. This part tells me to multiply the whole thing by 3. And this part says I'm going to have to change my index. This is a time advance by 1, it looks like. So I'm going to have to replace, let's call this a time advance by 1. So we're going to have to replace all the n's are going to have to replace with n plus 1 in that function. So we're going to have a 3, we're going to have an n plus 1, we're going to have our 1/3 raised to the n plus 1 power, u of n plus 1. So this is the function whose discrete time Fourier transform is this one up in here. So that's an example. We can use it in the forward transform, we can use it in the inverse transform. Now there's a duality in the discrete time Fourier transform, just like there is in the continuous time transform. So if there's a time effect, there's also an analogous frequency effect. We looked at what happened if I shift a function in time. We can ask the similar question of what happens if I take a discrete time Fourier transform and shift it in frequency. So if x sub n is the inverse discrete time Fourier transform of capital X sub f, we're asking the question, what if I take that transform and now shift it to the right by f0? And what happens is our original time function is multiplied by e to the plus j 2 pi n times f0, where f0 is the amount of frequency shift we applied. Now, what does this mean? This means that if I take my discrete time Fourier transform and move it to the right, I'm taking my time function, which is usually a real valued function, and now multiplying it by a complex exponential, an e to the j omega, which is a complex function, which makes my real function now complex as well. And so my time domain function is complex, which is also due to the fact that our discrete time Fourier transform, if we had started out with one that was symmetric, had the proper symmetry around f equals 0 for a real function, when I shifted it over, it lost that symmetry. And so it has to belong to a complex time function. What that means, again, multiplying a time function by a complex exponential means that we're going to take that original time function and multiply it by a cosine, at least the real part by a cosine, and we're going to have an imaginary part that is that original signal multiplied by j sine 2 pi n f0. Now, we generally don't like complex time functions, and so we can actually derive a more useful property and a more useful theorem for discrete time Fourier transforms if we make two copies. If we frequency shift our function, our discrete time Fourier transform twice, or move it plus and minus f0, move it to the right by f0, move it to the left by f0. So we're applying two different frequency shifts simultaneously. So take some discrete time Fourier transform, which has all the right symmetry for a real valued time function, delay it or shift it to the right by f0, which means this time function now is multiplied by e to the plus j and f0. Take another copy of this and shift it to the left by f0 so that it belongs to a time function x of n e to the minus j 2 pi n f0, and add these together to make a composite signal that has a transform that has peaks in both plus and minus f0. And what we've created in the time domain is the sum of these two signals, which is just x of n times e to the plus j 2 pi n f0 plus e to the minus j 2 pi n f0, which you recognize this as an Euler identity for a cosine, well, actually 2 cosine. And so doing this sequence of operations, taking an original DTFT of some real valued function, shifting it up by f0, shifting it down by f0, combining them together creates a new time signal that's, again, a real valued function. There's no j's in here anymore. But what I've done is taken my original signal, doubled it, and multiplied it by a cosine whose frequency is exactly the frequency I shifted my spectra to. Now, we don't want that factor of 2 in there, so for our property, we'll actually take that out and say it's not really frequency shifts that we were after. We were really trying to explain what happens over here in the time domain. If I take a time signal and multiply it by a discrete time cosine, that time signal is going to have some spectrum. If I multiply it by a cosine, we call that modulating, which is in this modulation function, this cosine has a discrete time Fourier transform that's a pair of impulses at plus or minus f0 with a weight of 1/2. When I multiply these in the time domain, I get a signal whose envelope follows the original signal, but it's a exponential, excuse me, a sinusoid rattling back and forth beneath that signal. This signal, this modulated signal, has a DTFT that looks like the original signal's spectrum, now split and shifted up and down by f0. This is the modulation property. This is what happens to signals when we multiply any time domain signal by a cosine. We take its spectrum, cut it in half, shift it up by f0, shift it down by f0. That's in fact how AM radio works, except not in the discrete time version, in the continuous time version. Now, important to notice, we did multiplication in the time domain, but if we look at these different signals in the frequency domain that were going on simultaneously, we took this spectrum, we applied this signal to it, and got this spectrum. Hopefully you would recognize that what happened here, if I think operationally, this function was convolved with each of these two impulses to create these two copies. That's how convolution with impulses work. We make copies of our original signal, center them on the location of the impulse, and scale its amplitude by the weight of the impulse. So we take this x of f, scale it by 1/2, center it on f0, do the same on this side, minus f0, and these should be capital F0s, and produce this new spectrum. And that then gives rise to the multiplication property of discrete-time Fourier transforms, which is extremely important. That if I have two time functions, like we had our original x sub n and a cosine, but it's true for any two-time functions. If I multiply them together and then take the product and take its DTFT will look like the convolution of the individual Fourier transforms, the individual DTFTs of our x and our g function. Except, now this was a result that we also saw in continuous time Fourier transforms. There's a difference here, though, in discrete time, because remember, our discrete time Fourier transforms are periodic functions. So this convolution I do is periodic convolution. So multiplying two time domain functions and then taking its DTFT results in a spectrum that is the convolution of the repeating spectrum, which is saying it's the circular convolution of x sub f and g of f, because they are forever long repeating periodic signals. So the only kind of convolution we can do is circular convolution. All right, well, in continuous time systems, this wasn't really the property that we were interested in. We were interested in its dual, which is, let me flip the operations around in the different domains. Let's do the multiplication in the DTFT domain and see what that gives rise to back in the time domain. And in this case, multiplying two DTFTs together gives us, if we inverse discrete Fourier transform that product, we get what looks like the linear convolution of the original signal x sub n and g of n. This then, as it did in continuous time systems, is what unlocks system analysis for us using DTFT transforms. For system analysis, we need convolution of an input signal with its unit sample response to determine the output of the signal. We could do that by doing convolution in the time domain, or pick the whole problem up, move it to the DTFT domain, where it becomes multiplication of two periodic complex functions, which actually still remains to be usually mathematically easier than trying to conduct the convolution in the time domain. So this convolution property says the way we can approach system analysis, where you give me x, you give me the system so that I can find h of n. I've got to find the output of the system for that given input. We could do it by time domain convolution, or move the whole problem over into the DTFT domain, where we can compute the output as the product of the discrete time Fourier transform of the input and the discrete time Fourier transform of the unit sample response. Now, remembering though that these are two complex functions, and so that multiplication implies for the magnitude of the output signal, it's going to be the product of the magnitudes of x and the magnitude of h, and the phase angle of the complex Fourier transform of the output signal is going to be the sum of the angle of x added to the angle of h. Now, if we approach system analysis this way, we can determine the Fourier transform of the output. I'm not done yet. I want that signal back in the time domain. That's where I want my answer. And so there's another step implied that we will use an inverse transform to get back to the time domain. And so our method then, when we want to do system analysis, is take x sub n, take its discrete time Fourier transform to get x sub f, take the h of n, take its discrete time Fourier transform to find h of f, or as we'll see in a minute, get h of f from the difference equation. Then determine the discrete time Fourier transform of the output by simply multiplying together, not convolving, but multiplying x of f and h of f. That gives me the Fourier transform, the discrete time Fourier transform of the output signal. I want to know its time domain equivalent, so we inverse discrete Fourier transform, again using tables probably, maybe partial fraction expansion, but some simple mathematics in order to get back to the time domain, which enables us to do convolution without doing convolution. We've done the equivalent operation in another domain. That's how we're going to want to do that. That will work anytime the convolution will work. So that will work for any system analysis of a linear time invariant system that's relaxed. And the thing we're calling the frequency response, h of f, is in fact the discrete time Fourier transform of the unit sample response. So yes, good news. That means you don't really have to do convolution, at least not analytical forms of convolution, to do system analysis anymore. We have this better method. And we can do it one better. We can find a simple way to find h of f, the missing link here, without actually having to first find the impulse response, the unit sample response. All we have to do is discrete time Fourier transform the difference equation. And that's what we were alluding to in this third option for how to determine the frequency response of a system. We're going to take the DTFT of the difference equation, apply the time shift property and the convolution property to tell us how to relate the output to input. So it's going to be based on our convolution property and also based on our time shift property that we can do this. So we have this relationship now that if h of f, x of f, and y of f are the discrete time Fourier transforms of h of n, x of n, and y of n, instead of doing convolution in the time domain to find the output signal, we can do multiplication in the frequency domain to find the DTFT of the output signal. But that also means in the discrete time Fourier transform domain, the frequency response is the ratio of the output signal's discrete time Fourier transform and the input signal's discrete time Fourier transform. Where do I get these guys from? Well, that's exactly what the difference equation tells me. It tells me the relationship between the output and the input. We need that relationship in the DTFT domain, though. So we take the difference equation and take its discrete time Fourier transform term by term, applying the shift property wherever we need to. So y of n's discrete time Fourier transform is y of f. Y of n minus 1's discrete time Fourier transform is y of f times e to the minus j 2 pi 1f with the time shift property. And if we multiply by a scalar a1 in the time domain, we multiply by the same scalar in the frequency domain. Similarly, a2 y of n minus 2 comes across as y of f times a2 e to the minus j 2 pi 2f, and so on. Do the same to the x side. b0 of x of n is b0 capital X of f. b1 x of n minus 1 is b1 e to the minus j 1f times x of f, and so on, applying the time shift property again. Factor out the y of f's we have from all the terms on the left, all the x of f's from all the terms we have on the right, and then create the ratio y of f over x of f that is, in fact, the frequency response of the system. And it turns out to be these terms from the right side of the equation divided by these terms from the left side of the equation, always. So as a quick example to finish up with, for our recursive filter, it has a difference equation y of n equals or minus alpha y of n minus 1 equals x of n. Discrete time Fourier transform that, y of n becomes y of f, minus alpha y of n minus 1 becomes minus alpha e to the minus j 2 pi f for that delay, times y of f, and x of n becomes x of f. Rearrange, we'll first pull out the y of f's from the common term from the left side, and then set up this ratio. H of f is y of f over x sub f, which means we'll have 1 on that side over 1 minus alpha e to the minus j 2 pi f on that side, which is exactly the frequency response for this system that we've derived in the past by several other methods. Although I would argue this is, other than looking it up in the lookup table, this is pretty easy. And that particular function, we've already looked at its magnitude and phase. If we wanted to plot those, the magnitude of this complex function is the magnitude of the numerator divided by the magnitude of the denominator, where the magnitude of the numerator is 1. The magnitude of the denominator has a complex component. So we break up the Euler identity into cosine minus j sine, group the real parts and the imaginary parts, take the magnitude by the square of the real part squared plus the imaginary part squared, FOIL out this square to get 1 minus 2 times 1/2 cosine 2 pi f plus 1/4 cosine squared 2 pi f, square the sine term, we get a cosine squared plus sine squared, leaving us just a quarter. Add it to the 1 to get 5/4, minus the cosine 2 pi f, square root in the denominator, 1 in the numerator. And there's a function of frequency, a real valued function of frequency that we can plot for the magnitude response of the system. And the phase of a complex ratio of two complex functions is the angle of the numerator minus the angle of the denominator. The numerator is 1, which is a positive real value, so it has a 0 phase angle. And the denominator has a phase angle. Well, again, we have to break this up into real and imaginary parts, so we do that again. You have the real part and the imaginary part. Looks like we'll have to use an inverse tangent for that. So this angle is the inverse tangent of the imaginary part over the real part. Because it's in the denominator, we're subtracting it. And so the total phase is going to be the negative of that inverse tangent. And when we plot those two functions, they look like this. So that's how we apply properties. They've brought us to the place now where with the convolution property, with the time shift property, we can now do system analysis on linear time invariant systems very quickly. We can find the frequency response directly from the difference equation through some transforms in algebra. We can use the convolution property to take the discrete time Fourier transform of input, apply it to that frequency response, use our tables to inverse transform the result, and we have the output signal in the time domain. So that's where we'll pick up next time. We'll go through some examples of how we're going to apply this in system analysis, see it at work. For now, we'll stop there.